What if an artificial intelligence could detect bacteria like Helicobacter pylori faster than a human? For this hackathon, we developed an AI model capable of identifying the presence of Helicobacter pylori from microscopic images.
This is a real image taken under a microscope. Hidden within it is one of the most common and dangerous bacteria in the digestive system, Helicobacter pylori. It is estimated that over 50% of the world's population carries it, and it is linked to chronic gastritis, ulcers, and in severe cases, stomach cancer. But diagnosing it visually is a challenge. Doctors must analyze dozens or even hundreds of microscope images, which is slow, exhausting, and prone to error.
This is where artificial intelligence comes in. Our proposal aims to be an automated support tool capable of detecting H. pylori in seconds, helping to reduce diagnostic time and increasing accuracy.
General research flow diagram, dataset contraction, image scaling, multiple image slices, generate synthetic images, dataset partitioning, train classifier model, finally interpretation and evaluation. Dataset contraction. To build our dataset, we use the Helicobacter pylori image set from IEEE data board. Each image came with coordinates indicating the location of bacteria. Using this information, we divided the images into two parts, one containing bacteria and the other without. This way, we created two balanced sets of 974 images, each one with H. pylori and one without the bacteria. Image scaling. Next, we enhance the quality of the images using the real ESRCEN super resolution model. We scale the images to 3.5 times their original size, generating new datasets with greater detail and sharpness. Thus, we ended up with 4 datasets in total, original and scaled images, both with and without the presence of H. pylori. Multiple image slices. Afterwards, we reset the images so that one of their size measured 512 pixels. From there, we crop them into 512 by 512 pixel segments. For the upscale images, we additionally apply a 25% overlap between crops to maximize the available visual information. Generate synthetic images. We also attempted to generate synthetic images using style GAN3 based on the original 512 by 512 pixel crops. Also, we managed to create new examples. Specialists discarded these images because they did not accurately reflect reality, mainly due to limited computational resource. Therefore, the synthetic images were not used in the final training. Dataset partitioning. For the final dataset, we selected 5,000 images with H. pylori and 5,000 without, combining original and scale crops. We split the data into 90% for training and 10% for testing. Within the 90% training set, we reserved a portion for validation, and as a result, we ended up with 7,200 images for training, 1,798 for validation, and 1,002 for testing. Train classifier model. We trained the model using 512 by 512 pixel images with a batch size of 32 up to 20 epochs and a dropout rate of 0.3. We tested different learning rates using the Adam optimizer and applied transfer learning with DenseNet 1-to-1 and insertion v3. In total, we generate 6 different models, combining architectures and learning rates. Interpretation and evaluation. Finally, we evaluated the models using metrics such as accuracy, F1 score, recall, precision, and AUCROC. This allowed us to determine which model offered the best performance for detecting H. pylori.
Now, let's look at the results of our approach. A total of 6 models were trained using 2 different convolutional neural network architectures, DenseNet 1-to-1 and Inception v3. The hyperparameters used were the following. The DenseNet 1-to-1 and the Inception v3 models were used for model generation, with a 512 by 512 image size, a patch size of 32, 20 epochs, a dropout rate of 0.3, a learning rate of 0.0001, 0.0005, and 0.001, and an Adam optimizer. For both the DenseNet and Inception v3 models, the 5 standard metrics were used for evaluation: accuracy, precision, recall, F1 score, and agrog, the results of which are shown in the tables. Overall, the DenseNet 1-to-1 model based models perform better in almost all the metrics analyzed. For example, model M3 stands out in particular, achieving the highest values for accuracy, recall, F1 score, and outlook, demonstrating its ability to correctly classify, identify true positives, and maintain a good balance between precision and completeness. On the other hand, although model M4 showed a slightly higher precision, this specific benefit did not extend to the other metrics. Its low recall value indicates a tendency to omit positive cases, which limits its performance in contexts where these errors can be critical. In conclusion, model M3 which belongs to DenseNet 1-to-1, emerges as the most robust and balanced, making it the most suitable option for real-world applications that demand both high precision and sensitivity. We can affirm this because it was able to identify a greater number of positive cases without significantly compromising accuracy. Furthermore, its outlook was the highest of the three models, reinforcing its ability to correctly discriminate between classes. The false rate was 7.29%, while the false negative rate was 6.89%, indicating a lower tendency to misclassify positive and negative images.
Finally, we built a chatbot that uses documents we previously uploaded in various formats. These documents are converted into vector using Amazon Python Text version 2 and stores in Pinecone to form the chatbot's knowledge base. When the user asks a question, the system links it to previous results about Helicobacter pylori, generates related questions, retrieves and re-ranks the most relevant fragments, and sends them, along with the original query, to Method Llama 3 model with 70 billion parameters. This entire process is part of what's known as retrieval augmented generation. Welcome to the Ronsoco Labs page usage flow. First, open the Image Classifier tab, select your BIOS image file, and watch the preview appear on the screen. Once the image is fully loaded, click the red Classify button to start the AI analysis. In just a few seconds, our AI processes your sample and displays the result. No Helicobacter pylori detected with 99.5% confidence. This instant diagnosis saves you time. To learn more, click Chatbot and type your question. What are the causes of Helicobacter pylori? Our virtual assistant will immediately provide a detailed explanation of how this bacterium is transmitted, its risk factors, and recommend follow steps.
Now, more than ever, this project has the potential to scale and make a real impact. Imagine it in rural clinics, where access to specialists is limited, or in telemedicine systems, where a fast diagnosis can make all the difference. Even in high-volume labs, this model could help optimize time and reduce human error. But it's just the beginning. With more data, our model can become more accurate and adapt to detect new bacteria or different types of microscopic exams. And with validation from medical experts, we can take it a step further, making it a reliable tool in real clinical settings. Imagine a future where every microscope has an AI assistant standing right next to the doctor. That future isn't far off. And with projects like this, we're one step closer to make it real. Thank you for watching our project and join us on this journey where we combine science, healthcare, and technology. AI with purpose, AI that saves lives.